Alright, welcome to lesson 11.3. This has perhaps the most intimidating title of all the lessons that I've given so far: permutations, combinations, and probability of non-overlapping events. Well, don't get too worried, because I'm just going to show you the basics of what could be somewhat complicated topics, but I'm going to just hit you with just a little bit of each one. First off, a permutation is an arrangement of objects in which order is important. So here's my example. I've got the letters A, B, and C. I'm going to write out the 6 permutations of the letters. So that means I'm going to put them in the orders, different ways that I can do it. For example, I could have A, B, C. That would be an easy one. Or I could have A, C, B. Or I could have B, A, C. Or I could have B, C, A. Or I could have CAB, or I could have CBA. There are no other distinct arrangements of those 3 letters. There are 6 permutations. Okay? Now, the multiplication principle of counting that we had a couple units ago, we can use those to count permutations. Remember, there's 3 letters. We're only going to use each letter one time, so there's 3 different ways I could put the first letter. There's 2 ways I could put the second, because I already have one there, and that leaves 1 way I could put the third. And if we multiply, notice I get the number of permutations there are. There are 6 of them. Now notice this 3 times 2 times 1. For these kinds of problems, this occurs quite a bit, so it has its own name. We use the exclamation point to represent that. It's called a factorial. 3 factorial means 3 times 2 times 1. In fact, for any positive integer n factorial means the number times the next smaller times the next smaller times the next smaller, all the way down to 1. Now 0 factorial, to make sure that everything fits its form and the patterns hold true, we define 0 factorial as 1, even though it doesn't fit this part here. This is like its own little separate special definition. So now I'm going to evaluate each one of these factorials. 2 factorial means 2 times 1, or just 2. 5 factorial means 5 times 4 times 3 times 2 times 1. That's 20, 60, 120. 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. Now on scientific calculators, you will even find a factorial button to make this a little bit easier. So I'm going to see if I can do this one. It's been a while. Let's see, it'd be 120, it'd be 720. That'd be 5,040 if I did this right. I hope I did. You can check my work. Okay, let's consider this example and see if we can find the number of permutations here. There are 10 students in class. The teacher needed to choose 3 students for class president, vice president, and treasurer. How many ways can the teacher select the 3 students? Well, I'm going to use the multiplication principle of counting again. And there are 10 different people that could be the president. That would leave 9 people that could be the vice president. That would leave 8 people that could be the treasurer. And if I multiply these together, I get 720 different ways, 720 different permutations of 10 students, 3 at a time. Now, permutations are, there's a formula right here, and I'm going to show you how I'm going to get the same answer using the formula. The number of permutations of n objects taken r at a time can be written like this, with a capital P in the middle, little n in front, little r, like subscripts here. And this is equal to n factorial, the first number factorial, all over n minus r factorial. So let me go back to this problem up here. If I have 10 things 3 at a time, that means I'm finding the permutation of 10 things 3 at a time. This is 10 factorial, using this formula, all over 10 minus 3, which is 7 factorial. So those are big numbers. This is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All over 7 times 6 times 5 times 4 times 3 times 2 times 1. I don't want to multiply that out. This was over 5,000 the last time. But look, I don't have to. These are going to all cancel factors, common factors, top and bottom. And then I leave 10 times 9 times 8, or 720 ways. Either way I work the problem out. So this case right here, I just did it. This is equal to 720. 5 things taken 5 at a time, well, this would be equal to 5 factorial all over 5 minus 5, which is 0 factorial. This is 5 times 4 times 3 times 2 times 1. I think we did that before, was 120. I defined 0 factorial as 1, so this is 120. Now this one looks monstrous. 70 things taken 2 at a time. Well, according to this formula right here, this is 70 factorial all over 70 minus 2, which would be 68 factorial. Now, stay with me. 70 factorial is 70 times 69 times 68, and so on, so on, so on. So times 68 factorial all over 68 factorial. These are going to cancel. I just have 70 times 69, that's a 0. That's a 3, carry a 6, that's a 48. 4,830 permutations, 70 things taken 2 at a time. Now, this works very nicely, order mattered. The 3 students that I picked, if I pick Manny, Mo, and Jack, president, vice president, secretary, that's different than if I went Jack, Manny, Mo, because Jack's now the president. So order matters there. Okay, now let's go back to this problem, but let's change it. We're going to change the problem here at the top of the board. Instead of the 3 students being given different offices, president, vice president, and treasurer, let's say we just put these 3 students to form a committee. How many different ways can the teacher select the 3 students? Well, here order doesn't matter. Because if I pick Manny, Mo, then Jack, that's the same as if I pick Jack, then Manny, then Mo. It's the same 3 people on the committee. So this is not quite the same. This is going to be a little different. This is going to be what we call a combination. Now I have the definition here with the formula, which hopefully you can read. I'm going to bring it up here in just a second. But we're going to take 10 students, 3 at a time, but not find the permutation. We're going to find the combination. To find the number of combinations of n objects taken r at a time, divide the number of permutations of the n objects taken r at a time by r factorial. So I have an extra r factorial in the denominator. Look at this formula here, and look at this formula here. By the way, these formulas are presently on the proficiency exam, on the formula sheet, and they do have a tendency to try to use problems from these. This is a combination, order does not matter. This is a permutation, order does matter. So let's go back to the problem here. We're going to take 10 things, 3 at a time, to form the committee. This is, using this formula, 10 factorial all over 3 factorial times 7 factorial. Now remember what I did before. I had 10 times 9 times 8 times 7 and so on. That'd be 7 factorial all over 3 factorial times 7 factorial. Well, 3 times 2 times 1 and 7 factorial. Those are going to cancel. That's 3 goes into 3 once, goes into 9 3 times. 2 goes into that once, goes into 10 5 times. 5 times 3 times 8. That's 120. That was the 720 that I got this way, divided by 3 factorial, divided by 6. That's 120. So there are less combinations than there are permutations because order does not matter. Okay, let's find here the combination of 6 things taken 3 at a time. 6 objects taken 3 at a time. This is equal to, remember the formula that I just had written down, 6 factorial all over 3 factorial times 6 minus 3, which is 3 factorial. So this is 6 times 5 times 4 times, I'm going to write 3 factorial, all over 3 times 2 times 1 times this 3 factorial. That's 6, and it ends up equaling 20. The combination of 4 things taken 4 at a time, this is 4 factorial all over 4 factorial. 4 minus 4 times 0 factorial. Of course, that's 1. And those are 1, so I just end up with 1 way. There's one combination of taking 4 things from 4 things. Now, we use permutations, combinations, to find the number of ways certain things can happen, certain events can occur. Of course, when you're doing that, you're right there next to probability. And we've already looked at some very basic theoretical probability in a previous unit, but what we're going to do is just extend on it just a little bit, not very much. We're going to consider the probability of 2 events occurring. Now these 2 events might affect one another or overlap, or these 2 events might not affect one another, or non-overlapping, or they're called disjoint events. The probability of disjoint events, for two disjoint events, the probability that either one of the events occurs is the sum of the probability. Most times if we have more than one probability, we're multiplying, but not on this situation. If A and B are disjoint events, then the probability that A plus B, one of the two, is the probability of A plus the probability of B. 50 tickets are sold for a raffle. You can buy 2 tickets, or you buy 2 tickets and your friend buys 3 tickets. One ticket is randomly chosen as the winning ticket. What is the probability that you or your friend wins the raffle? Well, the probability that you win the raffle would be 2 out of 50. The probability your friend wins would be 3 out of 50. So the probability that you or your friend wins would be 5 out of 50, or 1/10. 10% if you want to write it as a percent. And that's an example of finding the probability of 2 disjoint sets. Alright, so look this over and practice, practice, practice.